Chapter 9, Linear Momentum and Collisions. In this chapter, I want to talk about the relation between the mass and the velocity of the object. And also, we talk about the collision, elastic collision, and non-elastic collision. Now, linear momentum is P. It's a vector quantity which relates the mass of the object to the velocity. Let's take an object with a velocity v and mass m. So P has the same direction with v. Okay, P and v. So in this case, P is like this. The unit of P, m in kilogram, v in meter per second. This is the unit of P. Here we have the vector quantity in function of the components. We have x, y, and z components. We can say P, we have px plus py, okay, just x and y equals to m, and v has two components, vx and vy. So in this case we can say px equals to mvx and py equals to mvy. In the case of one dimension, we can say px without vector because it's in function of I. So px equals to mvx and py equals to mvy. What is the relation between Newton and momentum? You know, Newton's law, Newton's second law, summation of F equals to ma equals to m, and a is the derivative of the velocity dv divided by dt. M is a constant value. You can put m here. So we get mv divided by dt. mv equals to p. So equals to dp divided by dt. This is the relation between F and the momentum dp dt. Conservation of linear momentum. Let's say we have an isolated system. Inside we have two particles or many particles. Let's say at inside we have particles 1 and 2. Okay, at time initial, the mass m1 has a velocity v1, and the mass m2 has a velocity v2, and at time final, m1 M1 has V prime 1 and M2 has V prime 2. So in this case, we have a conservation of linear momentum at any time. What it means that the linear momentum must be constant at any time. So P for the initial time equals to P at the final time equals to constant. Initially, we have M1 V1 and M2 V2. So M1 V1 plus M1 M2 V2, and at the final time, at time t final, we have V prime 1 and V prime 2. So we have M1 V prime 1 plus M2 V prime 2 equals to constant. You can say this is the relation of the conservation of linear momentum. This is the first one, and you can write uh, delta P equals to O. So P final minus P initial equals to O. We get the same relation because V final here equals to P initial, okay, equals constant. We get the same result. In this chapter, I want to study only one dimension, uh, in the only one dimension. I don't take two dimensions. So here, when I say M1 V1, it can be V1X maybe or Y, okay? It's the same. Or we can take Y at the same time. I don't take a two-dimensional collision. Let's take, we have the initial and the final system. So of the particles, M1 and M2. So M1 V1 plus M2 V2 equals to M1 V prime 1 plus M2 V prime 2. If I give an example, here we have the object 1 with a velocity V1 and an object 2 with a velocity V2. Let's say V1 in the positive direction equals to 5 m per second, and V2 in the negative direction equals to 10 in the direction of minus I. If I want to substitute the value of V1 and V2 in the equation, you write M1 times 5 and M2 minus 10 equals, you continue. Why? Because this equation is a vectorial equation. It's like this. And here we can add I. So here we have M1 times 5I. And here I equals to M2 times minus 10I. As we have a one-dimensional study, we don't need to put I. Okay? And we can write the relation like this. But it's important here to put the value with the direction, minus or positive, in the general relation here, general equation.